Okay, students, so we're going to talk about um, doing a hypothesis test for means today. And we're working with our number of hours of sleep that you get every night. And we started this on Friday. We got the data that you all needed, and we put it in this into our data sheet. And I took that, and then I went to Staplet and entered the data into Staplet. And we got a mean of 6.4 and a standard deviation of 0.966 for the number of hours of sleep. And so I'm just going to use what Statmatic has for the answers that I usually share with you. I'm just going to use that today. I've been trying to do this other ways, so I'm writing on it. And with it being on the computer, makes it kind of tough. So I'm going to do it this way, at least for now, and we'll see if I can figure out a better way to do it. So you can see that we've got our mean and standard deviation here once again. So that is a reminder, this was our sample mean, so that would be X bar and sigma and S, excuse me, not sigma, but S. All right, so we state our appropriate hypothesis for the significance test. Our the mean is equal to 8 is our assumption, and the alternative is going to be that it is less than 8 because because we figure that they are getting less than 8 hours of sleep a night. All right. So the mean in this case, so mu is the true mean hours of sleep for AP Stat students at Grass Lake. So this is data about us. So because it's just data about us, then when we start talking about the conditions being met, then we know that that's going to be a whole nother issue. So is it random? No, it wasn't random. I guess you could say that we chose each of you randomly for our data, but probably not really random. We don't have 10% because there was more than 10% of you. We did it. And we don't have normal in this situation either, or we do have normal in this situation, even though the central limit theorem is not met because we had less than 30. But if we look back again at our dot plot, we can see that there is not overly skewed. There's no outliers in this case, so we could use that. All right, and when we get done, I'm going to talk about one of the things that they mentioned that we could say in this case, and maybe they mention it here. So, all right, so we give our formulas for the mean and standard deviation. So the mean of the X bar is just equal to mu, which we say is 8. Our standard deviation for our population, which would be the standard deviation of the means, right? Sigma divided by the square root of n. But since we didn't have the population data, just a sample, we do S of x divided by the square root of n. So in our problem, I did that, right? And we had 0.966 was our standard deviation divided by the square root of 10. So our standard error in this case is 0.305, right? And so we use that, and you'll notice that they did do a drawing here that here's our normal distribution, but it's not a normal distribution now. It is what we call a t distribution. So we're going to do t in the degrees of freedom. And so if you remember when we talked about degrees of freedom, then it was n minus 1. So this would be, we would have t and then parentheses 9 here because we had 10 pieces of data and minus the 1. I've actually been collecting data for tomorrow's lesson on body temperatures, and don't forget to add yours to that sheet. You can see that we have 3 people who have added theirs, but don't forget to add yours here. But I've also had people from all over the world right now that are adding data to that through a Google form that I put out on Facebook to a couple different groups and on Twitter. So you'll be able to see that when I get done with that. So, all right. So anyways, we found our t-value here, and I'll show you how to do that in just a minute. And remember, since we're working with means, the test statistic is a t-value. So we can use table B or we can use our calculator. And you can see here that we can go to our degrees of freedom, n minus 1 find the closest t value. Or on our calculator, they tell us we can use TCDF and lower, upper, and degrees of freedom, and I'm going to go through that. But we could also just do a t-test. So with your calculator, if you go to test, right, you can just choose a t-test, which was number 2 there. And we have, I did put the data in my calculator so you can see what we've got here, that our assumed mean was 8. Our mean that we got from our data is 6.4. There's our standard deviation, so I'm going to go down and calculate it. I got less than the mean. So when we calculate that, here's the numbers that we get. All right, t is negative 5.237, and our p-value then is 2.68 times 10 to the negative 4th, which is really small. It's approximately 0. So our conclusion then, all right, so our p-value is approximately 0, so you should put on your paper then your p-value is 0.000268. All right, so we are going to reject the null because our p-value is less than 0.05 and make the statement that, all right, so since our p-value is 0.0068, which is less than alpha 0.05, we reject the null. So therefore, we have convincing evidence that the amount of sleep for Grass Lake's AP Statistics students is going to be less than 8 hours of sleep. Right. So there's our walking through each of the steps. Now, when we do our work tomorrow, we will have independence for our conditions being met, and 10% would definitely be there, but we're also going to definitely have n is greater than or equal to 30. All right, so here's our main ideas then, but a reminder that here you have t is equal to x bar minus mu. So basically it's almost the same formula as for z. All right. So when we look at our notes for today's lesson, and this was before they updated it, so add these over here onto our sheet, and I'll post this for you also so you have it. All right, so our conditions, once again, random, normal, so the population is normal. They either tell us that it's normal, or we can use the central limit theorem if it's greater than or equal to 30, or we can look at our dot plot or histogram to see that it's there's no strong skew or outliers, and our normal 10%. So our test statistic in this case is t equals x bar minus mu over s of x divided by the square root of n. And make sure you draw the graph and shade it in. If it's going to be less than or greater than, make sure you shade the right side of that. But unlike normal, or where with normal, we would put the mean and standard deviation. When it's a t statistic, then we're just going to do degrees of freedom. Right? And then we can use table B with the degrees of freedom and the tail probability. Or you can use the TCDF, which they show, which is here. And I did not show you that, but you could do that. Or I suggest you just use the t-test, and that would be the easiest for you to do that. So, all right, so go ahead and do the check your understanding, and I'm going to post the answers here just a second. So you're going to want to pause the video, see if you can go through and do as much as you can on the check your understanding, and then check your answer. So I'm going to pull that up. So once again, pause it, and I will put the answer here for you. All right, so here they're talking about the level of dissolved oxygen in a stream of a river is an important indicator of water's ability to support aquatic life. Researcher measures the DO level at 30 randomly chosen locations. So we got our N is 30, so that's great because we can use the central limit theorem for normal. Here are the results of the milligrams per liter. So make sure you remember to put units in everything you're doing. Like in our sleep thing, we should have made sure you had hours there. So their X bar is 4.77 and the standard deviation 0.939. And the average dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So here they're saying that if we have less than 5 milligrams per liter, aquatic life is at risk. So we're checking to see if it's less than 5 because we want it to be greater than 5, at least 5 or greater than 5. Do the data provide convincing evidence that alpha equals 0.05 significance level that the aquatic life is stream at risk? All right, so our true mean of the DO level is what we're looking for our parameter. The null is there at 5 and the alternative is less than 5. Their statistic, X bar 4.77 and alpha level 0.05. All right, so this is a one sample t-test for the mean. All right, in this case, they do tell us that they were randomly chosen. All right, so it says 30 randomly chosen, so we have a random condition. 30 is probably less than 1/10 of all locations. Once again, we have normal because they did 30, so by central limit theorem, so we don't need to worry about that. All right, here's the general rule, specific rule, and then when they found their t-value in negative 1.33, so that's probably not going to give us our p-value. Then it's probably not going to be too small then in this case because we know if we had a z-value of negative 1.33, then that's pretty close to the mean. So we probably have a situation where it's not statistically significant. So when they tell us that here, that it is actually 0.097, and so assuming the mean DO level is 5 milligrams per liter, there's a 0.9097 probability again, the sample mean 4.77 purely by chance. All right, so since that's greater than 0.05, it's not statistically significant, and so we will fail to reject the null, and we do not have convincing evidence against the null or for the alternative. All right, so there's today's lesson, and you don't need to, once you've written this down, I don't need to see a copy of that. I just need to see your homework. And once again, make sure you get your data in for your body temperature, and have a great day.